Hey everyone, and welcome to this explainer. Today, we're cracking open the ultimate statistical detective tool for financial analysts, hypothesis testing. Look, in the world of finance, we're constantly bombarded with data, massive claims, and frankly, a lot of wild theories. But how do we actually know what's real and what's just random noise? Well, that's exactly where hypothesis testing comes to the rescue. It gives us a rock-solid, objective, mathematical framework to figure out if the evidence actually backs up the hype. Okay, let's dive into our roadmap for today. We're going to cover the 6 steps of testing, unpack errors in test power, dive into hypothesis tests for means and then variances, and finally wrap it up by comparing parametric versus non-parametric tests. Simple enough, right? Let's get right onto it. So think about this for a second. How do financial analysts separate pure luck from actual undeniable skill? I mean, if a mutual fund manager crushes the market for 2 years straight, are they a certified genius, or do they just flip a really lucky coin? Well, statistical inference is how we uncover the truth hidden inside all that financial data. It's basically the process of making probability-based judgments about a massive population by looking at a much smaller sample of observations. Which brings us to part 1, the 6 steps of testing. Think of this as our foundational blueprint. Now, to make these judgments effectively, we can't just, wing it. We need a rigorous, completely repeatable procedure. And it all kicks off with our hypotheses. We always state 2 of them. First up is the null hypothesis. We call that H0. And then the alternative hypothesis, or HA. You can think of the null hypothesis as the innocent until proven guilty baseline. Or in finance terms, this flashy new trading strategy is absolute garbage until the data proves otherwise. It's the status quo, the statement we assume is true unless our sample gives us incredibly convincing evidence to the contrary. Actually, as analysts, the null hypothesis is usually the exact thing we are actively trying to reject in favor of our alternative theory. So, how does this all build into a standard testing approach? Well, here is the precise 6-step framework we use for testing financial data. Steps 1 and 2, state your hypotheses, then pick the right test statistic and its probability distribution. Steps 3 and 4 are all about boundaries. You decide exactly how much proof you need by setting your significance level, and then state your decision rules, which gives you those all-important critical values. And then we get to the fun part, steps 5 and 6. You crunch the data to calculate the test statistic, and you make your final call. You compare your calculated statistic directly to your critical value, and boom, you either reject the null hypothesis or you fail to reject it. It's a beautifully orderly procedure, really. But, of course, it's not foolproof. Let's move on to our second topic, errors and test power, or the inherent risks of the game. Look, even with a perfect process, the math can totally mislead us sometimes. There's always drama and risk when you're dealing with probability. There are 4 possible outcomes to any hypothesis test, right? But 2 of them are outright errors. If the null hypothesis is actually true, but we mistakenly reject it, we've committed a type 1 error. That's a false positive. It's the ultimate false alarm. It's like when you think you finally found the next Warren Buffett, but it turns out they were just riding a lucky streak. On the flip side, if the null hypothesis is actually false, but our data totally fails to reject it, we've made a type 2 error, a false negative. In that case, we completely missed a genuinely good opportunity. Obviously, we want to make the right call, which brings us to an absolutely crucial concept, the power of a test. This is our ability to successfully catch a false status quo. Basically, it's the mathematical probability of correctly rejecting the null hypothesis when it is in fact completely false. Put another way, this is the strength of our statistical radar to actually detect a winning investment strategy when there genuinely is one. So, the million-dollar question is how we manage the probabilities of these errors. The probability of a type 1 error is called alpha, which also happens to be our level of significance. The probability of a type 2 error, that's called beta. And they operate on a very strict seesaw trade-off. If we want to be super careful and decrease alpha, say dropping our significance level from 5% down to 1% just to avoid those false alarms, we naturally increase beta. That means we'll reject the null less frequently, and as a result, we'll miss more true discoveries. The absolutely only way to cheat this seesaw trade-off and reduce both errors at the exact same time, you guessed it, gather more data. Increasing your sample size, your N, is literally the statistical equivalent of turning on more lights in a dark room. All right, moving right along to part 3, hypothesis tests for means. It's time to actually open up the toolkit. Now that we've got the blueprint and the risks down, we can start pulling specific mathematical tools, starting with tests concerning averages, which we use all the time for returns in finance. Depending on what exactly you're trying to test, you have to grab the right tool.
For example, when we're testing a single mean, like, say, checking if a January effect trading strategy actually yields an average return greater than 0, we have to look at the population variance. The catch? In almost all real-world finance scenarios, the true population standard deviation is just completely unknown. And because of that unknown, we have to reach for the t-distribution, calculating a t-statistic with n-1 degrees of freedom. But what if we want to compare two totally different means? Let's say we're comparing the historical returns of two competing mutual funds. First, we have to ask ourselves, are these samples independent or dependent? If they're independent, meaning the returns of Fund A have absolutely no relation to the returns of Fund B, we use a t-test that pools the variance of the two samples. But if those samples are dependent or somehow related, like maybe we're testing the exact same fund's returns before and after a major management change, then we use paired comparisons of the mean differences.
Next up, Part 4, Hypothesis Test for Variances. We're talking about measuring volatility here. You know, means are great for telling us about returns, but in finance, we care just as much about risk, right? Let's shift gears to testing volatility and variance. Think of this as your quick reference guide for risk. If you are testing the variance of a single normally distributed population, for example, checking to see if a fund's volatility has breached a strict 4% trigger level, you're going to reach for the chi-square test statistic with n-1 degrees of freedom. However, if you are comparing the differences in variances between two independent populations, you reach for the f-test. The f-statistic is actually pretty straightforward. It's simply a ratio of the two sample variances. And finally, let's look at Part 5, Parametric versus non-parametric tests. It all comes down to your assumptions. We have covered a lot of powerful tools today, but before we wrap up, we really need to talk about the instruction manual, specifically the underlying assumptions required to use these tools responsibly. Almost everything we've talked about today, the t-tests, the chi-square, the f-tests, these are all parametric tests. A parametric test is highly specific. It assumes right out of the gate that your data follows a certain probability distribution, usually a perfectly normal bell-shaped curve. But let's be real, financial data isn't always perfectly normal, is it? Sometimes it's heavily skewed or it has massive fat tails. Fun fact, assuming normalcy when you absolutely shouldn't have was actually a major mathematical driver of the 2008 financial crisis. So when your data violates those assumptions, you have to pivot to non-parametric tests. These are your distribution-free tools. They make minimal assumptions about the population, which ensures you don't accidentally draw wildly false conclusions from extremely messy data. And that brings us to a final, really important thought. You now have the analyst's toolkit. You know the 6 steps, you totally understand the trade-offs between type 1 and type 2 errors, and you know exactly whether to grab a t-test for means or an f-test for variances. But remember, the math is literally only as good as the data you feed into it. So you have the statistical tools, but will you always remember to question the underlying assumptions of your data? Because I promise you, in financial analysis, assuming your data is normal when it isn't is the single quickest way to turn a statistically significant finding into a remarkably expensive mistake. Definitely keep that in mind the next time you're staring down a massive data set. Thanks so much for joining me on this explainer, and keep questioning the data.